Somewhere in my classroom, I have a very large, heavy, perimeter-weighted bicycle wheel that looks something like this one. And there's a demonstration I like to do where I give this bicycle wheel a spin, maybe in this direction. Just grab it with one hand by the handle, and then with the other hand, grab the rim of the wheel and fling it and give it a large value of omega in this direction. Now let's make a XYZ axis for reference before we get too far in this conversation. Let's say the handle points along the x-axis. And then also in the plane of this page is the y-axis. So then the z-axis would be out of the page. Okay? So based on the right-hand rule, what's the direction of this wheel's angular momentum vector? In other words, if angular momentum is a vector, that's just equal to rotational inertia times the vector angular velocity. The angular momentum and the angular velocity share the same direction, and that direction is given by the right-hand rule. It just says take your right hand, curl your fingers to mimic the rotation of the bike wheel, and I think you'll find that your thumb points which way? Doesn't your thumb point like that direction? So that vector is the initial angular momentum of this wheel. Now maybe if there's a fair amount of friction in the bearings, that angular momentum is going to decrease as the wheel spins down. So the demonstration goes something like this. There's a piece of string, and I guess there's a little hook or something like that. And so the string is connected to the wheel. You grab it and you give it a spin as indicated, and then with one hand you hold on to this string, and then there's a net external torque on the whole system. There's a force of gravity, and as we know, we can treat it as if gravity acts entirely at the center of mass of an object. So there's this downward force equal to mg pulling down, and that force is at a distance of r, right? So if we measure from this axis of rotation to the point where the gravity force is applied, there's a lever arm of r and an angle of 90 degrees between that lever arm and the force. So there's a net external torque on this whole system. All right, well, what ends up happening is the wheel undergoes a type of motion known as precession. If an eyeball were to look down the y-axis, here's what it might see. So now looking down the y-axis, we see the z-axis this way, and the x-axis this way, and the z-axis this way. Oops. And then the wheel is here with the two handles. Well, I guess the wheel wasn't quite that far over, was it? The wheel is maybe here. And there's one of the handles, there's the other handle. And we said the angular momentum vector points down the x-axis. And then we're looking directly down the string. So that blue dot is the string. Well, the precession is something like this. The wheel starts to go around in a circle this way. In other words, the handle turns to here, and the wheel moves into this position. And then a moment later, the handle's pointing this way, and the wheel's now here. And the path of the wheel traces out this circle. The reason is because a net external torque produces a change in angular momentum. You might think of Newton's second law of motion for translation as the sum of all external force is equal to mass times acceleration. But we restated that at one point during the semester as the sum of all external force is the time rate of change of linear momentum. Now keep in mind, if linear momentum is mv, this all agrees, right? We're saying we're taking the time rate of change of mass times velocity, and by the product rule, that's m dv dt plus v dm dt. And as long as we deal with objects that don't have any rate of change of mass, then that term goes to 0, and we're just left with m dv dt, which is ma. So this expression for net force agrees with the first expression for net force. So what's the rotational equivalent to that equation? We think that net torque is equal to I alpha, but I think it might be better to say net torque equals the time rate of change of angular momentum. And by the way, if angular momentum is I omega, then if we take the derivative, if we take dl dt, that's d dt of the product of I and omega, which gives us I times d omega dt plus omega times di dt. And if we deal with objects that don't have a rate of change of their rotational inertia, then we're just left with I alpha. So there we have it. Anytime there's a net external force on a system, there's a rate of change of the angular momentum. And by the way, the direction of the torque vector is in the same direction as the change in angular momentum vector. So, what is the direction of our net external torque? Well, external torque is also the cross product of lever arm with force. So use that other right hand rule that says point the fingers of your right hand in the direction of the lever arm. In other words, point the fingers of your right hand in the direction of this pink vector. So your fingers are pointing to the right, and now rotate your fingers until they point downward in the direction of the force, and you see that your thumb points along, I guess this is the negative z-axis. So that's the direction of the change in the angular momentum. So what we have is an initial angular momentum pointing down the x-axis and a change in angular momentum pointing down the negative z-axis. Well, that's kind of what this picture is saying. I'll draw it again down below. This is again the bird's eye view. So an eyeball looking down the string that supports the handle of the wheel sees it like this. You see the x-axis and you see the z-axis. There's the handle of the bike wheel, and there's the initial angular momentum vector, and then there's a change in angular momentum that I guess this is the negative z-axis. So there's a little change in angular momentum pointing this way, because that's the same direction as the external torque. That's what we mean when we say Newton's second law can be expressed as the vector net torque is equal to dl dt. The direction of the change in angular momentum is the same as the direction of the external torque. And the external torque is due to a lever arm of R crossed into a force that points downward. Okay, so as you know, vectors don't change when you move them to another point in space. As long as you keep a vector of the same length and pointing in the same direction, it's still the same vector. So if we have a vector pointing this way that represents the initial angular momentum, and then we add to it a tiny little change in angular momentum that points this way, then that results in a final angular momentum pointing in this direction. And then what happens is that external torque doesn't go away. The force of gravity continues to point downward, but now the lever arm no longer points straight down the x-axis. The lever arm points a little bit into the first quadrant, And so that changes the direction of the external torque. The external torque now points a little bit into the second quadrant. So the change in angular momentum now points this way. So there's the next little dl. And next thing you know, then the angular momentum now points here. And what's the result of that? Well, then again, the lever arm no longer points down the x-axis or even in the first quadrant. Now the handle, the lever arm, is pointing directly up this axis. And so the change in angular momentum just keeps adding. And we get another little dl, which leads to an angular momentum. And so you see what happens is the angular momentum itself traces out a circle, and this is why the wheel starts to spin around and precess in this manner. So what we want to figure out is another value of omega. Lowercase omega represents the number of RPMs with which the bike wheel is spinning, but then at the rate it's spinning on its own axis. But then we want to know at what rate does this precess around the string. So we'll call that capital omega. And Greek letter omega, when capitalized, has this horseshoe shape. So we're going to define capital omega as the precession angular velocity. So what is that value? Let's go back to net torque equals dl dt. So the net torque is due to the force of gravity acting at a lever arm of r. So again, let me draw the bike wheel, remind you what I'm talking about. If we say the handle on the bike wheel has a length of r, and the force of gravity is a torque-producing force about this axis of rotation, then that net torque is the product of mg, the lever arm, and then the sine of 90 degrees. And so that's equal to dl dt. Okay, well, the initial angular momentum vector pointed down the x-axis and is equal to I, the rotational inertia of the wheel, times omega. So let's look at that picture again of the bird's eye view looking down the string. We see that same angular momentum vector pointing down the x-axis, and then the angular momentum vector traces out a circle. So the length of the angular momentum vector doesn't change, just its direction is changing. And it changes due to this little quantity dl. Well, okay. Just as motion around a circle, if this is the unit circle right here, if we say an object has traveled a displacement s in comparison to a radius r, we say s is equal to theta r. I guess if this is a dl, this is a little d theta. So I think that same equation can be stated analogously as dl equals L naught d theta, right? dl is to s as r is to L naught. So we have mgr is equal to dl dt. This is a way of stating Newton's second law as net torque equals the time rate of change of angular momentum. But then again, dl is L naught d theta. So mgr equals L naught d theta dt. Okay, mg times r is equal to, well, L naught is I lowercase omega, and then we're left with a d theta dt. But d theta dt would be a way of describing the rate at which this angular momentum vector is tracing out a circular path. And that's exactly what we mean when we talk about capital omega, the precession angular velocity. So the net external torque, mgr, is equal to I omega multiplied by the precession rate of rotation. So lastly, the rate at which the bicycle wheel precesses is equal to mgr over I omega. Or we could just simplify and say it's equal to the net torque divided by the initial angular momentum. Now what does that mean? There's an inverse relationship between capital omega and lowercase omega, right? The rate at which the bike wheel is spinning on its own axis is in the denominator of this equation. So the faster the bike wheel spins on its own axis, the smaller the rate of precession. Okay, so there you have it. Make sure that you watch the video that I've added to this unit. I believe it's called, what is it? Maybe bicycle wheel gyroscope? No, I'm not sure. But I have a demonstration that I've linked and added to this unit 4.2 where you can see the behavior of a bicycle wheel as it precesses.